Good morning, everybody. Let me just erase that. Let's see, I think it's February 24th, 2014. Another screencast. We're going to look at, actually I'm starting a series of these, the whole purpose of which is to demonstrate how to apply the Common Core mathematical practices, the 8 of those. We'll discuss it as they come up. Of course, not every lesson will utilize all 8, but that's okay. So we're going to look today at the issue of similarity and how it plays out in problem solving and the big ideas. Let's begin with the simplest of all figures, let's say a 1 by 1 square, whose area is 1 square unit. If we stretch that and double all the dimensions, so now it's 2 by 2, then students should feel comfortable that the original area has not been doubled, but rather quadrupled. So the area of the second square to the area of the first square is 2 to 1. No, it's not. 2 to 1, quantity squared. This is the relationship we want them to see. They will say doubled, but we want them to realize it's raised to the second power. That may not be immediately apparent, but if we expand it to a ratio of 3 to 1, so we'll multiply this dimension by 3, and we'll multiply this dimension by 3. We produce a square whose sides are now 3 times the original. So the ratio of the area of the new square to the original is 3 to 1, quantity squared. Again, if we ask the students, they'll say it's 9 times, we hope. But through patterning and regularity and repetition, we hope that they will see a more advanced relationship here. Also, the perimeters. The perimeter of the original square was 1. The perimeter of the 2 by 2 square is 4. And the, no, that's wrong. Let's go back. The perimeter of the original square is 4. The perimeter of the 2 by 2 square is 8. And the perimeter of the 3 by 3 square is 12. So the ratio here of the perimeters is the same as the ratio of the sides. Or we could say raised to the first power. That's important. We're trying to get them to recognize that this is a linear relationship, not a quadratic or square relationship. That is, the perimeter varies directly as the sides, and similarly for the third square compared to the first square. 12 to 4, 3 to 1. So this demonstrates that the perimeters are in the relationship according to the side. So perimeter of figure 1 to the perimeter of figure 2 is side 1 to side 2 for squares, which are similar figures. And we're using squares as the springboard for this because it's the most it's most common figure, it's easiest to see. And it appears that the relationship between the areas is not a linear relationship. It's area figure 1 to area figure 2 side 1 to side 2 quantity squared. Now they may not see the square relationship immediately, that's why you need to do a few of these. If you only do 4 to 1, they'll think it's doubling. But then when they realize it's not 6 to 1, it's 9 to 1. And you could ask them, why does that make sense? Why does it make sense that we're squaring? And we would want them to begin to understand that it's related to the fact that area is given by base times height, or in the case of a square, s squared. So it's not shocking that the relationship between the areas will be a square relationship. Furthermore, area is measured in square units. If this is 1 square unit, it kind of makes sense that we're looking at not 2 units or doubling, but rather 2 squared, 4 square units. But that's critical. Here's a relationship that students know early on in upper elementary school and middle school, and it translates into this proportion. If the area varies directly as the square of the side, that means the ratio of the areas of these similar figures, or squares in this case, equals the square of the ratio. Alright, well, we've talked now about squares. Let's move on to triangles. So, I think what we'll do here is we'll add another page. Now let's look at a triangle, connect the midpoints. This is the simplest way of, well, this is the analog of the square problem. We're doubling the sides, so if this is x, this will be 2x. This is y. This will be 2y. We could sit here and count squares, since this sketch paper I'm writing on actually is grid paper, and younger children can do that. But we also know that we have similar triangles here. X to 2x, y to 2y. Included angles are congruent, they're the same angle, reflexive. And so the remaining side, I'll call it B instead of Z. Those sides will also be in the ratio 1 to 2, since they are similar triangles. So one way of seeing that square relationship again is to compare the two triangles, triangle 1 and triangle 2. So the ratio of their areas is 1/2 base times the height, and the second one is 1/2 its base, 2b, times its height, 2h. Where did that come from? Well, again, if the triangles are similar, then it's reasonable to suspect that this will be 2h, but that also follows from our similar triangles. And you know, if figures are similar, then corresponding segments will be similar, but you could prove that a number of different ways. Alright, so where are we here? We're looking at the ratio of the areas of the similar triangles, and the 1/2s, the constants, drop out. That's important, because whenever you're dealing with some kind of a relationship like this, whether it be linear or quadratic, and there's some constant, there's some coefficient in the ratio, it will drop out. And when we get to circles, it will be pi r squared over pi new radius squared, so the pi's will cancel out. This is getting them to think of the bigger ideas and ask questions and lead them toward that. The b's and the h's will go out, and we're left with a 1 on top over 2 times 2, which is 1/4. But what's another way to write that, folks? We're right back to our square relationship. So even for similar triangles it works, and we could demonstrate this with other figures. Well, let's look at it from another point of view. Using multiple representations, or what math people are now calling the rule of 4, we could have looked at that midpoint problem another way, and that is locate the third midpoint, connect the midpoints, dividing the triangle into 4 triangles. We know, or we can justify that this triangle here would be similar to this triangle. They are and that's something you can discuss with them. Again, if this was x and y, and this is x, and this is say z, call it z this time, we know this is also z because the whole side was 2z, remember? So we can demonstrate that these triangles are congruent. In fact, all 4 triangles are congruent. So this would be a visual approach. And once again, we'd have the area of the small triangle to the big triangle is the ratio of the sides quantity squared. This is the big idea here. And when we demonstrate repeated reasoning, we're helping them recognize it. And this type of regularity is one of the 8 mathematical practices. We want them to demonstrate it, so we have to demonstrate it as well. And we create an environment in which they will begin to recognize it and be asked to see this and generalize it. Let's move on. We could go on to similar triangles, but this time we could divide the sides into 3 equal parts, or trisect them, if you will. Get rid of that. Okay. So we have x, but this time we have 3x. And we have y and 3y. Again, by similar triangle considerations, this triangle is similar to the big one. So the ratio of the areas of the small to the big is 1 to 3. Or is it? We hope they are catching your mistake. Sometimes I make these mistakes intentionally, and sometimes they're unintentional. Well, boys and girls, if we know the ratio is 1 to 9, what does that mean about dividing up the big triangle? Yeah, we should be able to divide this into 9 congruent parts. Well, let's get the trisection points down here. Start connecting those like we connected the midpoints. It's kind of fun when you think about it. Am I done here? I guess I have to do that. And now they could see that there are 9 congruent triangles. We haven't justified they're congruent, but we're going to move on. And kind of an interesting relationship going on here. Notice this part of the diagram is the previous setup when we had a 1 to 2 ratio. We're just stretching this, right? So it's building on the previous diagram, so we're actually setting up a recursive relationship, a repetitive relationship that is building on the previous step. And notice that there was one triangle in the top row here, 3 triangles here. We didn't mention that before, did we? And 5 triangles here. What a coincidence, right? That those numbers add up to a perfect square, just like 1 plus 3 adds up to 2 squared. Wouldn't you hope that somebody recognizes that? And if not, we need to promote it. Now keep that in mind. I wonder if that's a coincidence. Let's go on. Do one more of these. We'll do a Quadra section. Divide each side into 4 equal parts. We'll bisect and then bisect again and again. And again, we could do that to the base. We could prove this using the similar triangle relationships, but why not let students, and someone will volunteer to come up and want to show that there are 16 of these smaller triangles. Not much of an artist here, folks. So we have 1, 3, 5, 7, for a total of 16. Or we could reason area of small to area of big is 1 to 4. Quantity squared, which is 1 to 16. We could do this by the area formula again. So we have 1/2 base times height to 1/2 4 base 4 height, and we see our 1 over 4 times 4, 1 over 4 squared. They'll just want to write 1/16. It's our job to write it like this. So what did we talk about today? Let's go back to the beginning. Our first screen. Why did I start with, let's see if I can move this down. There we go. Why did I start with the squares? Because simplest figures, square units, and it relates to exponent 2. And we developed the concept that the ratio of the perimeters is the same as the ratio of corresponding sides, or another way to say that is the perimeter of a square is directly proportional to a side. See, there's your constant. Therefore, it leads to the proportional statement, P1 to P2 equals side 1 to side 2. And then we have the ratio of the areas, but just as the area is a square relationship in proportional statement, we get A1 to A2 is the square of corresponding sides, or square of the ratio of corresponding sides. What a huge idea that is. Then we went on to triangles. We used the midpoint connectors, a 1 to 2 relationship. We obtained 1/4. We're leading them to again recognize the square relationship. Not quite as obvious as it was for squares, but it came out the same way. And then we saw it visually. Very powerful. And we did it for a 1 to 3 relationship. We used a different similarity transformation. We stretched the sides by a factor of 3. Again, as with squares, we saw that the ratio of the areas is the square of the ratio of corresponding sides. We saw it visually. We began to see an interesting pattern here with the sum of consecutive odd numbers equaling a perfect square. And you can get them to formulate that, but we can't go off in too many different directions here. This is just something for them to look at and think about, and some will think about it when they leave the classroom and may want to explore it further. We did a 1-to-4 relationship. We developed it visually. We used the square rule, if you want to call it that, because that's the principle that we were getting to. And we also derived it algebraically. So regularity of reasoning, patterning, repetition. We want them to be able to abstract this, but we have to create that environment ourselves. Thank you.